So this is meant to be a bit of a light lecture this week, where I want to go over a few things. In fact, I'm going to do it all in lecture 6. Can you see lecture 6? Can someone unmute their microphone and tell me?
Yep.
Okay, great. So I wanted to talk a bit about the major components inside a horizontal axis wind turbine. So you have this is the hub at the front, so low speed shaft, and then it goes through a gearbox, which does not look like this. But there you go, essentially a bigger gear and then a smaller gear. And then through your generator, and this is where controller anemometer sits. Anemometers don't look like this as well. They all look like a little black box now. But this is a nice kind of the best represented little diagram on the internet. So, and then you have a yaw drive here, the brake with the caliper, like I explained to you in one of the videos, and it's sitting there on the high speed shaft. Gearbox is actually a planetary gear set. So the planetary gear set has, this would be a ring gear. And then you would have a sun gear. And it has its planetary gears on the outside. So that's what a gearbox, actually, the type of gearbox they use, because it has quite a large conversion ratio. So that's in general what's inside them. I wish I could take you inside a wind turbine like I have taken other classes, but it's just something that literally we can't do because it happens to be a confined space kind of field trip. But you've probably seen the scale of these in real life. They're so large that this compartment in here is actually a room, and a few people can fit in this room. There's usually a hatch on the top and a little spot where you see that you know, the people who are working in there, say, let's say changing the oil on this gearbox is a common thing they do. You can sit up on the top of this wind turbine and have your lunch up there. I'm sure you've seen pictures and YouTube videos of that. So they are a rather large, they're not really a device, they're actually a room. So the nacelle is essentially a giant room. I wanted to just fill you in a little bit on the blades. So a blade has a shape like this. And it's kind of like a tooth. And this is called the root of the blade. And this is the tip of the blade, and it's actually narrower here. If you were to take the cross section, and it is twisted. So I don't want to spend a lot of time on this, but I just want to talk quickly about why a blade is twisted. So we remember V equals omega R. So if something, let's say something is this shape and it's rotating at omega, then the V equals omega R. That's tangential velocity is equal to the rotational velocity times the radius. So that means here versus here would be different. Rotational velocity is the same, but radius is higher, therefore velocity would be higher because of the radius term. So the tangential velocity, let's do actually 3 of them. So the tangential velocity increases as you go further out from a point of rotation, right? This is R1, this is R2, and this is R3. So if we think of that as a blade, then whatever wind is hitting it is going to be faster at the tip than it is closer to the center of rotation if this is a blade. And that's not a good thing. You want the velocity across that blade to always be the same. All right, so if it is not twisted, now I'm going to take the cross section. And then I'm going to do a blade that's twisted. And I'm going to take a cross section. So hopefully you're following with me here. It's not something I'm going to test you on, but it is something I've tested in the past. But I just want you to understand why these airfoils are twisted. So if I were to section that same this same airfoil that I had here, so I sectioned it near the root, then obviously the blade would be thicker, and I could section it in the middle, and then it gets narrow at the tip. So this is the tip. So here's if it's not twisted. Whereas if it is twisted, then it's going to have an airfoil like this, an airfoil like this, and then I'm going to just draw it as an extreme. It twisted to the end, and it's actually like this. Any questions about cutting this section? Cutting a section near the root, cutting a section middle, and a section at the end. Any questions about what I've done there?
Which way is the wind?
So wind would come in here. And then the blade is going to be moving, right? And let's say the velocity of the blade, which is this velocity, goes this way, right? Goes up. So let's put the wind on each one of these then. Velocity of wind, would it be the same length on each of these? Would the wind have the same velocity?
Yes.
Of course, because you didn't change the wind, did you? Now let's add the velocity of the blade. See, it's going in this direction. Maybe we should choose a different color. Do that one in pink. Velocity of the blade. How is it here, big or small? Near the root. V equals omega r. Big or small?
Small.
It's small. Here, it's a bit bigger. Here, it's a bit bigger, right? And if we stop and think about it, and we would have to go back in our lectures to think about it and put these pieces together. But this is the angle, what did we call it? It's attack angle. Did we call it theta? Attack angle, or did we call that alpha? I think we called it alpha. Angle of attack, alpha. So here's angle of attack. What happened to my angle of attack?
Grew? It's larger?
Yeah, it has changed. All right. Now, what is happening here is when the velocity of the wind comes in, say we're going to have wind. Wind is going to be all the same, but what's going to happen is that
V blade is also going to be constant. Or at least consistent.
the velocity of the blade is going to be going in a different direction. So it's hard for me to draw it here. So it's going to be like this. Oops, that should be green. And then it's going to be like this. And then it's going to be larger, yes, but like this. Because of the shape of that airfoil. And then what you're left with is alpha, alpha, alpha. So alpha constant. And remember what the angle of attack, what's the relationship between power and angle of attack? Could you draw that curve? The maximum power, I always call maximum power point, and I don't even, you guys haven't really answered me about whether that's common for vocabulary for you, but the
It came
maximum
from solar. I noticed you guys didn't answer that. MPP is a form of tracker used for solar. But
yeah.
MPP is common in solar. I didn't know it was common in wind.
Well, I don't know. But it's a good description for, that's what I don't know either, but it's a good description for maximum power. Because there is a maximum power point on this curve, and it happens at A alpha, right? So only at this alpha is the happy point. Therefore, you need to design the shape of these blades so that this alpha stays right here. So I'm going into a little bit more detail than I probably have to, but that's why the blades are twisted. For your exam, know this. Okay, I'll move on before I talk too much. I want to draw a turbine here, and I want to go through just a few little labeling some components that I didn't put in your lecture. I always like to kind of draw the turbine, the entire turbine, and talk about all of the components. I don't have room for all of the blades here. So these blades would be attached to a hub. Well, it's actually called a rotor. So rotor means rotating parts. And it has a hub plus 3 blades. Oops. So let's talk about the blades a little bit. So the blades, they're strong, but they have to be light. They're hollow. They're a composite. They usually have 3 segments. You can find some YouTube videos of these blades moving on the highway. Maybe you've seen it actually in real life as well. So one transport truck takes each of the segments. A person can stand up in each of these segments. So they're hollow, and a person can literally stand in them. So they're quite large. So back to the rotor, which has a hub and 3 blades. The hub, you have to unfortunately access from outside. Does that appeal to anybody? But there shouldn't be a lot of maintenance required on it. There's pitch control. In the last quite a while now, 15 years, there has been pitch control. And that means that because of pitch control, and you know what pitch control is because you read the lecture, in advance. Basically, you need electric motors in.
So wait, reading the lecture is confusing, but most of the ones that are in Ontario now on these big farms, they do have pitch control or don't?
Yeah, they do.
Oh, okay.
Yeah, they never used to, but until the point of the efficiency being so good that now pitch control is worth it. So yeah, I understand that that wasn't really very clear. It's sort of the business case never used to be there because the efficiency gain from the pitch control and the cost of doing it wasn't worth it. Now, and they used to be hydraulic. But now there's electric motors in the hub. That can do pitch control, and that small gain in efficiency is worth it because we're reaching the BETS limit. And when you do that, they're called feathered. When you pitch these blades, they're called feathered blades. So you can turn them to catch the wind. So you can increase. You would be running it at maximum lift force, but really you feather to increase drag in shutdown.
Also, what I
Reason
was trying to picture, like you would feather if you're facing the wind, but you'd actually, if you're turning 90 degrees, you'd actually almost want to 90-degree your feathering as well, kind of actually, because then if you feather and you turn 90, you'd be back to like spinny, right?
Yeah, and I don't know the answer to that question. It's better when we can go on our on our field trip and you can ask people who live and breathe this every day questions like that. I don't know whether they feather first and that slows it down a bit and then they yaw out of the way. I don't know. But modern turbines, they do have the pitch and the yaw control is what I can tell you anyway. Over here, so this is the nacelle, which has to remind you of the Enterprise spaceship. But basically this has gearbox, generator, brake. Is that how you spell it? Brake. It also has heat exchangers because quite a lot of heat is generated inside that gearbox. It has active coolers. It actually has heaters as well, and the heaters are only for people. They're for people who go up there and have to work on the gears and everything in the winter time. And you'd have your yaw system up there. And the yaw system would have motors and gears. So you would have the output shaft of the gearbox going to the generator, of course. It also has a gantry.
What has motors and gears?
The yaw, sorry, the yaw system. Are you referring to my writing? The yaw system.
100% yes.
Isn't it terrible? Aren't I better on the board? All right. And something you might not know about is it does have a gantry crane. Why would you have a gantry crane?
Because stuff's heavy and you don't want to have it on your back going up a big ladder.
Yeah, so the gantry crane is sitting actually up there in the nacelle, right? And then it can pull things up and it can pull things over. And so it lets you lets you pull. Let's say you're doing a gearbox change out. Well, the gearbox isn't a little thing that you'd put on your back, right? You need that gantry crane to do that. And the gantry crane, it's interesting when you go inside these. Has anybody been in a wind turbine? No, it's interesting when you go inside them, that gantry crane also provides counterweight. And that's actually counterweight to yourself, to the human being that is climbing the series of ladders. So there's ladders, there's a hole in the floor, then there's another ladder. And this is a floor. And then you go through another one. You can stand on this floor, you can take a rest, you go through another ladder. But you have this counterweight system connected to your harness, and it pulls you up. And my students, usually when I bring them out to see one of these sites, they always ask, well, do you actually use that? And the answer is always, when everybody starts, they think they're too tough and they don't use the counterweight. But then the novelty wears off and you start using it. So I'm sure that's helpful once they've climbed a couple of 100 times. The diameter down here could be as big as 3 to 4 meters in diameter. There's literally a door, which you've seen. They're actually like little hobbit doors for you to go into, that always remains locked, and there's controls inside a room. There's a room in there that I would usually fit about 5 students in to look at the controls in there. Underneath, what you don't see, oh, and there's a lot of lag bolts. What you don't see is there's actually a massive foundation. There's large lateral forces, so this is really heavyweight. Because there's lateral forces. So this thing can't tip. So this foundation is around 15 meters by 15 meters by 9 meters deep. And the bolts that you see, if you visit a wind turbine, then you see there's just hundreds of bolts around here. And those bolts look pretty big in person. They actually go all the way through the whole foundation. So this is bolts throughout. So they're not messing around. With the security of these wind turbines. So those bolts go all the way through the 9 meter deep foundation. I need to talk about the tower itself. So the tower itself is structural. So it does provide structure. It's not just getting the nacelle up there. And you can see on YouTube when that structure fails, it's quite epic. They're tubular. They're rolled steel. They're short segments. They're around 20 meters segments. And they're bolted together. So this would be 20 meters. And those are separately trucked in. You might see those on the highway as well. And the height of the tower is approximately the diameter of the swept area A. And that's not how we draw it, is it? We usually draw a wind turbine as this big long pole and some blades at the top, but it's not like that. The blades go quite a distance down. So if this is your swept area, then this distance is the same here. So it actually goes halfway. So it's not just a big long pole with, if I call this diameter, then the height of this pole is the same as that diameter, the tower height. It's not just a big long pole with the blades way at the top. They actually do come halfway down that pole. So that's all I wanted to cover. If you have any questions, let me know right now because I want you to see some exam work.
Karen, what does it say under structural, under tower?
Tubular.
Thank you.
I don't think that clarifies things, does it? Writing on a vertical surface. Okay, any other questions? It's kind of fun. It's not nearly as fun as when we usually go to see some wind turbines. That's lots of fun. But I did post you a video in here that I like of somebody exploring a wind turbine. So look to that YouTube video if you want to have a bit of an experience with a wind turbine. All right, so this is a special treat. I've never done this before. But I'd like you to go into some groups and I would like you to work on some midterm questions. I'm giving you, in this course, I'm giving you the 2015 midterm. I'm not going to ask you about blade twist in this midterm, but it's good practice anyway. I took these pictures from a hard copy of the 2015 midterm just because I had to do it in a place where I didn't have any Wi-Fi. So excuse me for using my cell phone and sending myself a hard copy over data. So anyway, I will put you in 4 groups and you can take a look at this midterm. Don't forget that you can also take a look at the other pages of the midterm. In fact, I encourage you to look at all of these questions, not just the ones you're assigned to. Now I'll bring you back in 15 minutes, but please try to put answers to these.
Excuse me, Karen.
Go ahead.
Thank you.
I'm pretty sure I sifted out most of the pictures, so we're okay. I don't know how to do a slideshow, so we can just keep going. Oh, maybe I can, I don't know if I can like select all and open them all. Oh,
Somebody here.
okay. Let's go one by one. So yeah, like you can kind of see over here. Here's some of the blades. Is this easy to see?
Oh yeah, we're seeing
Yeah,
it.
we can see.
Okay, so yeah, you can see like there's the generator there, and then there's the blades are over here.
Where was this?
This was this was just near Strathroy. The wind site's called Bornish, and it was a Next Era project.
Oh,
And
okay.
this is kind of near their Jericho site too. We can close these. And then, yeah, here's a couple pictures of the turbine kind of being constructed.
Look
and
at
this
that
one kind of
crane, eh?
shows. So here's actually, this is a guy up here. So way up top, this guy is actually clipped on to the top, and then he's reaching out and grabbing onto this, like to the assembly. And there's actually another guy that you can't see on like a radio communicator, and he's talking to the ground guy and the guy in the crane that are guiding this like whole assembly in, and it literally just like interlocks, and everything just slides in nice and gently, and then they kind of attach it all. And I
Wow.
wonder if I have a better picture. It's kind of neat because they use actually more than one crane.
That's a nice
Um,
picture.
you can see these black bands.
Mm-hmm.
These are actually attached to smaller cranes that are just off in the distance here. And those are like RT, like rough terrain cranes that they'll use to kind of bring in some of the other equipment. What those do is those keep them up, like obviously you're holding the turbine up, right? So now the wind wants to take a hold of it. So they're on those to keep it stable as well.
Just two of them, Dylan?
Like to keep this axis good.
Yeah.
I'm sorry?
Just two, right? Not on all three blades, just on
Yeah,
two.
so you can see there, I can't see the one, I don't think there's was ever one on like the bottom. They would always pick it up from the main kind of hub here and then
That's
one
in-
on each of the upper tips. And then it's kind of neat because obviously no one's climbing out to unhook these. And so these are actually explosive charges and
Ah,
they will detonate when when they need them to, and that's what will release the cable. And it just like it's not a very large charge, but it's big enough that it goes. And then there are times where they don't release, and then they'll actually like disconnect from the crane, and then they'll let a technician go and deal with it later. But you'll see like some of the times you'll see these bands hanging with just a crane line hanging from it. It's kind of funny.
did you see that, Dylan? Did you see it detonate and release?
Yeah. It was pretty cool. You'll watch them, and you just kind of see it like drop from so far away.
So
Um,
cool.
See if I can find some more that are kind of neat. So before they put the tower on, we try to get some cable in, and it's kind of handy. So this is that concrete base that you were talking about, Karen, and then these are all those rods that go around. And then so you can actually like you can't stand up under here. I guess no, sorry. The tower would be the door would be at about the roof of the backhoe, and you would have this room under here is sort of like a basement where all your cable goes. So all the cables that run from the tower, they'll go out, and they actually there's you can kind of see it here. These conduits here, you'll pull the cable out through these conduits, and then it'll go into like a transformer that's just outside the tower here, and then cables will get trenched out from there on to the road kind of thing.
And that's why the door is so high, Dylan.
Yeah. So I guess here's a like this. So going back here, when you walk in here, you kind of like step down to about like this level. You can see where there's like the steps, and
Mhm.
then everything down below that is kind of like a below area where you kind of hunch over and shove all the cables through. But yeah, there's not much room. Like you're not standing up by any means. But just like another area that you don't typically see in when you're outside of one. Um, this might show, yeah. So here's where the transformer. So everyone like cables come down the tower into the lower area, out through conduits that are like poured into the with the concrete, and then those conduits feed into this where that the or that the transformer is placed on. That's a vault as well. And so there's actually like a concrete floor underground here, and those conduits come up the floor or out the side depending on how it was poured. And then you have your lines will go in here, and then you can see these cables are stubbed up here. Like that'll be for fiber that'll communicate with the towers to like for pitch control and stuff like that. It can handle all of those communications. And then right here, that's typically what they'll use to plow in the cable with. And it's the same plow essentially as like what they use for field tile in like in farmers fields. And yeah, and then they just basically drag all the cables out to the road underground. Well, plow them underground.
So Dylan, it looks in that picture, the wind turbines looked close together, but do you know how far apart they are in that picture?
Oh yeah, they're far apart. Um, they're not too far apart. Like typically what they'll do on a site, I could probably dig up an old map, but what they'll do on a site, I'll pull up the annotate, just draw like a little box. So if this is like a big site, they might have something like they'll have like a tower road typically. And so on that tower road, then they'll have like Tower 6, Tower 13, and like, I don't know, Tower 12. And you'll be like, why they have 12, 13, and 6 is because 6 was probably 14 and then 14 changed somewhere down the line and they had 6 available. It's some of the times the way things get numbered is a little bit of a free for all, just the same as anywhere else. But yeah, and then basically from there, it's nice because if you know you're going to like 12, you know you're going to like say Tower Road 14 or something like that. And then you know if you're going to Tower Road 14, you may have a crew that's at 6 that needs something as well. And then you're kind of able to support both by just knowing the plans a little bit. So as you get onto like jobs, just like when you work in any plants or anything, you'll learn like the grid mapping system and you kind of get more efficient that way.
And so, and this is called a plant, right? Do you call it a plant?
I guess I would call it more of a site. I would call like the stuff that's going underground the plant. Um, just because in terms of like underground, typically stuff that's buried, it's called like you're planting it there. Um, but yeah, for any wind turbine projects, I always call them like sites, really. Just like a solar, I would call it like a solar site or like a PV site, same kind of terminology. And then yeah, for this distance, honestly, you could probably have these like within 1,000 meters sometimes, but then they could be up to 3 kilometers apart. But typically, you'll they're all kind of close together here because it makes it easy to pull all the cables through. And then like this would be a small run of cables, this would be a small run of cables, this would be a small run of cables, and then they'll all join up into here in like a transformer at the tower road, and then they'll jet out at like a bigger series of cables from there. Same thing like what we've been learning with Charles too about distribution and everything. Yeah, anyways, so yeah, I don't want to eat up too much time, but I thought that was kind of cool to share and something a little different. So
No, this is perfect. You eat up as much time as you want. This is perfect and this is relevant.
but it is pretty fun. I know a lot of people like kind of wonder what you do on a wind site, and a lot of it's playing in the mud. If you kind of want to get into like the field side of stuff, there are a lot of days where you're literally stuck in the mud. So we got some good pictures of guys kind of being stuck lots of days. So this guy's pretty swamped. Actually, what they'll do is they'll build the road.
Don't think it's sharing.
Yeah, share again. We want to see them.
Oh no.
Another quick question, Dylan. Like, what was your role? Like, what job did you host? What was your day-to-day responsibilities?
Oh, I got a great picture.
Look at that.
There.
Nice.
My responsibility was to take this shovel right over here and to stick it in the ground. And if the metal part touched about there, that was deep enough, and we carried on. But it was I worked I was laboring for these guys on this site, so it was anything from like being in the trenches with the hose to actually like throwing the cable into the trench to working. Yeah, so here's like just kind of working with the machine, trenching in cables, and then we also worked with the directional, like my kind of specialty was with the drilling. So when there was a lot of like stuff in the way, or like typically this will probably be going under a creek. I think he was going under a creek and then through a field or a forest. So I was kind of smart on this end of things and knew how to put pipe underground. So that's why I was there. But really this job would take all like a week to get the pipe in the ground. So you're kind of doing other things while the process is happening. So yeah.
You have
Here's
quite an
a-
expertise for your age, Dylan.
Yeah. Well, I just look young.
You're wise and experienced. This is great. I'll need your address for the paycheck for this lecture.
Yeah, that's all right. It's consider it a donation.
That's fantastic. Well, I'm eager to see all of these pictures, but how cool. Okay, well, thank you. Thanks for enriching us there.
Yeah, yeah.
All right, well, we have to move on to more boring things, I guess. I'm going to stop this recording.